The title of the session is Process Integration and Deep Decarbonization. We put together a variety of speakers which for this session, which come from some different viewpoints. I'm going to let the speakers introduce themselves rather than me read a formal introduction for each. But our first speaker, I'm just mention is Raj from Armstrong International, doing really important work in process integration and where to look for heat pumps and where to look for heat reclaim. Ovais from UC Davis is partnered with his co-author, Steve Mulqueen, and they're going to be talking about the same thing, case study, which really gets us closer, I think, to where we need to go. Amit is going to be speaking from DNV, a little bit broader perspective, the DNV approach to the food sector, having done extensive work in there. And then Kevin Johnston from Total Energies is going to talk about bringing solar into these industrial customers because we certainly want to try to take as much carbon from the combustion processes as we can, but in the end, we need clean electricity. So I think it's a fantastic panel, and with no further ado, Raj, will you come up here and get us started?
A very good afternoon to everyone. I'm Raj. I lead the heat pump product line in Armstrong. In today's session, we will see about thermal decarbonization, how industrial heat pump helps thermal decarbonization, and how pinch methodology plays a role in it. I was very happy to see a few members talk about pinch methodology already. So that's one of the main topics today. I come from Armstrong International. We are a family-owned organization founded in 1900, more than a century-old company. We have 15 manufacturing locations around the globe. We claim ourselves as an experts in thermal utility optimization. Back in 2017, there was a strong requirement for heat pump in Armstrong Indian market area. And so we got into this heat pump product line in January 2017. And we can make a heat pump to generate a high temperature hot water of 248 degree Fahrenheit or steam of 248 degree Fahrenheit. Our maximum heating capacity is 7 million BTUs per hour, and the TRL is 9. We recently received a DOE grant to expand our manufacturing facility to manufacture industrial heat pump in Michigan to supply the heat pumps within the United States of America. Since we sell heat pumps, a very common inquiry these days is steam heat pump. Customer is having a steam boiler to generate 100 PSI of steam, and they ask us, like, can you give me a heat pump for 100 PSI of steam? We can do that with the help of a heat pump, a flash vessel, and a bunch of steam compressor, MVR in series, to give up to 100 PSI of steam. Now, when we submit an offer to them, customer feel that the CapEx is high, there are a lot of electrical equipments in this, the operating cost is high, the savings is low, and they don't prefer this particular schematic or the implementation of the heat pump system. And when we ask them, like, where do you take this 100 PSI to? They say that, we take 100 PSI to, at the point of use, we reduce that to 30 PSI. And so far, they keep, okay. Hello? So far, they kept their process information just like a black box. And when we asked really what is their actual pressure they need, they say like 30 PSI of steam in their process application. Then we gave heat pump design where we have a heat pump with only one steam compressor, MVR in series, to get it up to 30 PSI. Even in this case, the operating cost is not that lucrative, the CapEx is more, the savings is a bit better than the previous design. Then we really ask customer, like, can you open up and tell that what is your actual application is? They say that they take this 30 PSI of steam in a steam heat exchanger and heat the process liquid only up to 158 degree Fahrenheit. To heat a process liquid to 158 degree Fahrenheit, why do they need a steam heat pump? That to 100 psi, reduce it to 30 psi. So for this particular application, we proposed a heat pump, a high temperature pressurized hot water heat pump, which can generate high temperature hot water. They need to change the heat exchange design from steam to a hot water heat exchanger. It requires more surface area because in hot water you have only sensible heat. So customer is good with this because it's only one equipment to heat up the process liquid to 158 degree Fahrenheit. And the capex is lower because it's one equipment. Operating cost is lower, the savings is good. And customer finally decided to go with this. And since this is a high temperature heat pump, it has got a lot of funding opportunities and the incentives from the utility providers. When we go to the site to install this particular unit, to find a feasibility where we can install this unit, at that particular point of walkthrough, we see that there's a regenerative thermal oxidizer, which is sitting 50 feet away from where the heat pump will be installed. And that RTO is throwing about 320 degree Fahrenheit of waste heat to the atmosphere. In this facility, do they really need a heat pump? Why can't they just utilize the waste heat from RTO and heat up this process liquid to 158 degree Fahrenheit? They don't need a steam heat pump at all. As a manufacturer, I can close my eyes and say that there is no RTO there and we can still sell a heat pump and make money. In Armstrong, we believe that we want to do the right thing to the customer. So this particular facility, we would educate customer that do a direct heat recovery instead of going for a high temperature heat pump. Even though it is completely funded, but still do not go for it. So how we can identify whether the facility really requires a heat pump? Can they live with the direct heat recovery? In order to get that particular area, we need to do the pinch analysis, a pinch methodology. So pinch analysis will help us do you really need a heat pump? Or can you do a direct heat recovery and meet all your heating needs? Or a combination of both? So to do that analysis, we need to have a study on two things. One, what are the process heating requirement in the facility? So in x-axis, you can see the heating capacities in million BTUs and temperature in y-axis. This could be process A, where it requires heating from 60 to 100, process B, etc. So you plot all the heating requirements in a chart, and currently that could be, all this heating could be done with the help of a steam boiler, and the steam meets all the heating needs in the facility. Because of decarbonization, most of the customer jumps right into a steam heat pump, utilize their existing steam network. But we just saw that having a steam heat pump to generate a process to 140 or 100 degree Fahrenheit, it is not that efficient. So we can go for a mixture of low temperature hot water heat pump to heat up a process to a lower temperature, a medium temperature heat pump to a medium temperature requirement, and a high temperature heat pump for a high temperature requirement. These set of heat pumps would be more efficient when compared to a steam heat pump. And these heat pumps can be installed locally near to the process. Even though capex would be a bit higher in this case, but still these heat pump would be much efficient than a steam heat pump. The next study we need to know is that what are the waste heat which is available in the facility. When I say waste heat, it's nothing but a cooling which is required in a process. A specific process needs to heat it from 230 to 210, or another process need to be cooled down from 210 to 170. And all this heat or the cooling, which done on the process, or the waste heat from the process, is vented to the atmosphere with the help of a cooling tower or a chiller. Now, after doing this analysis on the heat source side and sink side, we can plot that in a curve and identify what is the pinch point is. So this is where we call this like a pinch temperature or pinch point, where the source comes close to a sink, and beyond this point and below this point, we can do a direct heat recovery. So for example, currently this particular process cooling is done with the help of a cooling tower. This process is heating done with the help of a heat pump. Instead of doing this, we can do a direct heat recovery, take this 230 degree Fahrenheit process liquid and heat up the process, another process from 160 to 180 degree Fahrenheit with the help of a shell and tube heat exchanger or a plate heat exchanger. You don't need an electricity to do this particular heat transfer, just a direct heat transfer. So likewise, above pinch point and below pinch point, do the direct heat recovery. And then what is left out is the remaining low-grade waste heat, where direct heat recovery is not possible, and they need a high-grade useful heat in their particular process. So that's where the heat pump comes into a picture. A heat pump can take the low-grade waste heat, which is left out in a facility, and it can convert into a high-grade useful heat and put back in the process. So after doing this pinch analysis, look at the optimized way. We are trying to utilize what are the waste heat which are available in the facility and heat up your existing process. So about 60 to 70% of the waste heat from the process went into the atmosphere with the help of a cooling tower or a chiller. Why can't we put back in the same process and optimize with 1 or 2 heat pumps? So we do this kind of a pinch analysis for different multinational companies across the globe. And this is one of the side where we plotted the source and sink, and you can see that there's no pinch point. This particular heating should be done with the help of a heat pump or any other heating technology. In this particular site, they have a pinch point, so above and below, we can do a direct heat recovery. The remaining of that particular heating should be done with the help of a heat pump. In the third site, you can see that there is a pinch point. All the heating need is met with the help of a direct heat recovery. In this particular site, they don't need a heat pump at all. But my biggest fear is that if I get an inquiry or in a bid specification, there's a heat pump, as a manufacturer, we try to educate the customer as much as possible, but if they keep everything as a black box, and if I try to sell a heat pump, we can make money. And I always get scared that, whether I'm selling a heat pump to a facility where they really need it, or they just want a heat pump to decarbonize certain amount of CO2 in their plant. So the pinch will help us to identify, do you really need a heat pump, or a combination of direct heat recovery and a heat pump, or there is no heat pump in there. There's no requirement for a heat pump in the particular facility. So that's how we educate customer about this pinch methodology. Before they even go for a heat pump implementation, it's quite important they do this pinch analysis and implement the heat pump technology in the facility. That's all I have from my side. Thank you.
So just to make sure we have adequate time for all of our speakers, I'm going to wait and ask you to hold your questions to the end, and then if we have some time, we could do that. But Raj, that was the most lucid explanation of one of the more complicated things we teach in engineering, which is pinch analysis, that I've ever heard. And you set the bar high for the next presenter, Ovais Khan. Ovais, come on up, all right, who's going to talk about his... Here you go. His experience applying this in much the same way as Raj. So please.
Hello, good afternoon, everyone. And thank you, Raj, for setting up the pinch technology. It just makes my presentation much easier to understand. So I'll be presenting today our recent decarbonization project that we did for a client, and we're calling this approach Intensifying Decarbonization Using Total System Integration. And I'm presenting here on behalf of my team, which is led by Steve Mulqueen in the fourth row right there, and Dr. Kissock sitting right here. So a little overview of this facility that we were looking at. They had an annual electricity consumption of around 38 million kilowatt hours, natural gas consumption of 170,000 million BTUs, resulting in about 19,000 metric tons of CO2. We were working at a meat processing facility, so the major systems at the plant were their meat processing infrastructure. They had an ammonia-based refrigeration system, an industrial hot water system with a temperature requirement of 130 degrees F, and they had a wastewater treatment and plant and office HVAC. Just laying out our decarbonization methodology, we split our methodology into 6 discrete steps. We start off with baselining our energy and emission use. Then we move on to energy efficiency opportunities. Then we move on to the next opportunity of heat integration and heat pumps. Then simulation of these options. Then we move on to identifying any clean electricity options, or how can the facility clean up its scope 2 emissions. And lastly, we provide our recommendations of all the previous bullet points in using a metric of levelized cost of avoided CO2, or LCAC. Starting off with the baseline from electricity, we identified that the biggest end use at the plant was their industrial refrigeration system. And within this system, their refrigeration compressors were the largest end use. Some of the other big end uses were compressed air and lighting, whereas on the natural gas side, it was surprising for us as well as the facility to find that more than half of their natural gas was going into space heating, and about 45%, which will be the blue, green, and red slices, goes into their hot water system. Similarly, we did a baseline for their emissions use, and here we found that there's an even 50-50, around 50-50 split between natural gas and electricity, and the specific end-use fractions are commensurate to their energy use fractions in the earlier slide. So moving on to our next step in the decarbonization process was to identify any hotspots and identify energy efficiency opportunities. Here we found, I won't go into much detail, but here we found that our biggest opportunities were in the efficient control and operation of the refrigeration system and the compressed air system. And we were able to take off a lot of electricity use by switching to LED lighting. On a total, we were able to save around 3.5 million kilowatt hours per year in electricity use, and we were able to reduce their emissions by 600 metric tons using energy efficiency recommendations. Next step was to see their heating and cooling loads and identify any heat reclaim, heat exchange, or heat pump opportunities at the facility. And for this, we identified, so on the right, this chart shows their heating demand and the heat they're rejecting at every hour of the day. So the purple line that's at the bottom, that's their heating demand for hot water, whereas the blue, the yellow, and the red are heat that they're rejecting from the refrigeration system. So, and each of those lines are different operating scenarios. For example, the blue is the winter, heat rejected in the winter, the yellow is heat rejected during shutdown, whereas the red one is heat rejected during summer operating modes. So here we can see that the plant is rejecting more heat than it is using to heat up its hot water. But this is a low temperature heat, so we cannot do direct heat exchange. But there's an opportunity to use a heat pump where we can extract all of that waste heat and use it to supply high temperature heat to our hot water. We call this a simple solution, using just a simple heat pump for this process. Why is this a simple solution? Because we've not evaluated any heat exchange possibilities up to this point. A couple of problems which were also highlighted by Raj earlier, going directly to a heat pump can give you is that you might oversize your heat pump when you don't need that heat pump capacity. And another is that you can see our heat loads, both heat rejected and heat required, are modulating or changing during the day as well as during different seasons. So trying to operate a heat pump with these changing conditions can prove to be a challenge. So our revised approach, much as described by Raj earlier, is using pinch analysis to come up with a total heat integration for the site, and not directly go to the heat pump solution. So when we did the pinch analysis for this facility, we found out that this is just showing one of the scenarios during summer production day, a typical summer production day. And we found out that we could use heat exchange to get to a water temperature of around 100 degrees. And then we only need the heat pump to get that final 30 degrees of heat. But this just shows one of the many conditions that can happen at the pond. So we needed to do multiple of these pinch analysis. We did, based on different seasons, we did one for summer, one for winter, and then we did another couple for sanitation. So there's production and sanitation in summer and winter. And through this, we tried to cover the whole 8760 or the whole year for the plant so that we can propose a solution that works throughout the year. A couple of things that we learned from this pinch analysis was that heat exchange is a viable option throughout the year. We have that overlap region throughout the year. And we have ample capacity on our source side to power any heat pump to supply to the hot water. And we have some extra that the facility can then evaluate for later use for their space heating or other heating needs. So using our pinch analysis, we came up with a system diagram for heat reclaim and heat reclaim with the heat pump option. So in our heat reclaim, what's going on is we're trying to capture that incremental temperature in series. So we first go to the subcooler, we get all the temperature we can out of there, all the energy we can get out of there. From the subcooler, we go to the condenser. From the condenser, we go to the oil coolers, and from the oil coolers, we go to the de-superheaters. And through this loop, we've captured all the temperatures in series, and we've captured as much energy as we could in our hot water system. And for our heat pump system, we again use the refrigeration system as source. We use a water-cooled condenser and a de-superheater to isolate our heat pump from the refrigeration system. We've also added strategic storage opportunities both for our heat pump solution and our heat reclaim solution, so the plant can operate these systems independent of each other and store heat when they have extra available and use it when they have low waste heat in their system. So through the use of all of our heat reclaim and the pinch analysis, we were able to come down from a simple solution of a 12 million BTU heat pump to a heat pump that would be half that size and use half that energy. So this saves on CapEx as well as operating costs for the facility going forward. Moving on, so we developed the pinch analysis, we developed the system integration designs. The next step was for us was to simulate these options and see how they were performing throughout the year. And we wanted to see this in detail because we were tying our heat pump system to the refrigeration system. So we wanted to see what the interaction was with when we were interacting with the industrial refrigeration system. We wanted to see how we were doing with transient or changing weather conditions and operating conditions. We wanted to see what heat pump size performs best if you're oversizing or undersizing the heat pump, and how are the part load efficiencies going through for our heat pump as well as our refrigeration system. And we want to see what is the optimum size or what storages should we have for our heat reclaim and our heat exchange loop. So to simulate this complex problem, what we did was we decided to write up a simulation software, and this is an object-oriented simulation software written in MATLAB, and it takes an Excel input sheet, and then you can simulate all of your different options for heat reclaim and heat pump. A little about how this software is working right now. So it's, you specify your devices, then your devices become part of a system, then your system becomes part of a measurement boundary, and you can have multiple of these measurement boundaries in your total simulation boundary. So for example, a refrigeration compressor is a device. It becomes part of your compressor system. Your compressor system is a part of your industrial refrigeration measurement boundary, and that measurement boundary can have a compressor system, a condenser system, a heat exchanger system, and so on. And another measurement boundary could be your industrial hot water measurement boundary. And we can simulate all of these different measurement boundaries within our total system boundary. So we use this software to simulate both our different options for heat reclaim and heat exchange. And our results were that we were able to reduce not only the natural gas consumption and the carbon emissions for the facility to a large extent, but we were able to do that at a negative levelized cost of avoided CO2. So a negative cost here means that you're saving carbon and you're also saving on your money. So, and just a point here that this facility is located in a region with a natural gas to electricity ratio of more than 4. So getting a revenue positive solution here was a confidence booster for us in heat pump technology. Moving on to our step 5, we then moved on to identifying any clean electricity options that we could suggest to the site. And here we identified a 2 megawatt plant that the facility could have of on-site solar, and based on their demand, they would be using almost all of this electricity. They can reduce their emissions by around 500 metric tons, 400 metric tons per year, and again, they would do this at a negative LCAC, which means that they're saving money and they're saving carbon. Lastly, we use a metric of LCAC to summarize all of our recommendations on a single summarized sheet. And through all of our recommendations, we were able to save around 4,000 metric tons for the facility, which comes out about 20% of their total CO2. And another thing we should note here is that the utility that the facility is taking electricity from has a decarbonization target of 2050. So their electricity emissions will get decarbonized in due course, but we were able to reduce their natural gas emissions to a very large extent through our projects here. A couple of more things here. All of our recommendations were revenue positive. So doing all of this, they save money and they save carbon. And they can also see which of our recommendations they should do first based on the LCAC metric right here. So the more the negative LCAC, the better the project is for you. And lastly, we also summarized our recommendations within the DOE industrial decarbonization pillars. I guess we heard from them earlier about this also. So here we see that energy efficiency recommendations are the best ones. Energy efficiency is king, and you should do energy efficiency first every time. But we also see that electrification and fuel switching, if done correctly, can also be revenue positive interventions for a facility. And lastly, one more thing I want to mention is you're seeing this big blue URL at the bottom. This is part of our other work with Lawrence Berkeley National Lab, where we are developing tools which can help you perform various steps of this decarbonization assessment. So you saw the Sankey diagram earlier in baselining of your emissions. Then we had the pinch analysis tool where you can generate your pinch analysis graphs. And then finally, we have this LCAC tool where you can generate these LCAC plots for your projects. And we also have an upcoming tool for electric load planning. And with that, thank you.
Wow, that's just fantastic work. All right, Amit, the bar is really hard. Hi, get up here. And so now we have Amit, he's the vice president from DNV, and he's going to talk about, I think, more broadly across the food sector. Please.
First of all, thank you, Kelly, for inviting me to speak at this conference. I'm glad to be here. Just a little bit about myself. As it says, I'm from DNV, and DNV is a consulting and advisory firm who serves commercial and industrial customers across the energy value chain. I also look at California EM&V work, statewide EM&V work, evaluating programs for all the utilities across California. Ram talked about more technology specific and heat pumps and how heat pumps could be used in a right way. And then Ovais kind of went through all different analysis. And maybe you all are like after your Indian food, I'll wake up and don't need a cup of coffee now. So I'll zoom out and talk a little bit about decarbonization in industrial sector, and specifically talking about an example for a food and beverage subsector. So with that, I'll just start with a bit of context, where, as you can see on the left side there, the chart there, the still industrial sector ranks second after transportation sector in terms of emissions. But if you look at the right-hand side, and you can see that chemical side on the top, and refinery, iron and steel, and food and beverage still ranks fourth. So we still have a lot of opportunities for food and beverage sector to decarbonize. And specifically in California, the emission of food and beverage sector is, if I recall correctly, is 3.3 million metric ton of CO2. So that's a huge amount of emission that's coming out of food and beverage sector. So that sets us up for our agenda today. We'll go through a little bit of background of food and beverage industry, and then we'll go over what are the temperature needs for food and beverage sectors, and what's our decarbonization approach to decarbonize an industrial facility, specifically a food and beverage sector. And then we can spend more time on talking about a specific example that DNV worked with a customer to achieving decarbonization for a food and beverage facility. And then we can wrap up with our learnings and conclusions, and open it up for questions. Again, quickly, I'll go over this chart. I stole this chart from AEO, as you can see on the left side, all the subsectors, that's under the food and beverage sectors, but on the right side, as we see a comparison between 2019 and 2022 about the emission by energy use. As you can see on the 2022, the overall emission has gone down, specifically for the electricity because of more energy efficiency and decarbonization efforts. And this is a carbon Sankey chart, as that shows total GHG emission on the right side. On the left side, it shows the offsite energy in trillion MMBT, trillion BTUs that goes into the food and beverage sector, and how much emission we really generate, which is 95.7 million metric ton, which is pretty much close to 10% of total industrial emission in the US. Typical temperature processes, I know a lot of audiences here are, either consultants or for, working with energy efficiency. We know the food and beverage sector is one of the sectors that doesn't require really high temperature ranges. Most of the temperature applications fall below 200 degrees centigrade. So as you can see, I've divided, both food and beverage, and we can see the temperature ranges for different unit operations, and we see most of them are below 200 degrees. And this slide shows that there are a lot of opportunities, as Ram said, for heat pump applications, right? Where we can electrify a lot of our heat, which is currently through fossil fuel, natural gas, and all other type of feedstocks. Now, let's look at how we go about a facility and perform decarbonization assessment. So if we look at it, our decarbonization efforts fall into 6 different categories, and this is nothing new, right? We have always done. If I remember my older days with working with in the ISC, you go do energy audits, look for opportunities, collect information, and come back and perform analysis, right? But we're looking at energy efficiency and waste reduction. But this is like zooming out, as I said earlier, and looking at a holistic perspective. Let's look at, nothing is off the table. We're looking at within the facility. We're also looking at, that's coming into the facility boundary. Also, things that, outside the facility boundary. Is it, downstream or upstream? So take everything into consideration so that we are looking at all the technology, all the finances, how we can get a customer to the level of decarbonization, whatever the goal is. So first set of goals is setting up initial target with a customer. Some customers might have a SBTi target setting already. Some might not have, but some might have some other type of science-based target. So work with them to clarify if there is a target, clarify the target, and get their emission plans, and then move on to the process and value chain analysis, where you go and find an energy champion. I always say about boardroom to the boiler room, right? Bringing those people together and making sure that all the things are at the table, all the opportunities are at the table. So basically doing a contextual analysis. And then once that's done, we'll have a lot of different set of opportunities. Then you move on to the technology assessment and forecast. This is more of collecting detailed data, taking the data into consideration, and performing analysis in terms of energy savings, carbon reduction, cost, all other key performance indicators that's needed by the facility. And then take all those and put it in different scenarios. So when I mean by scenarios, we're looking at a plan for 2040, achieving a carbon neutral goal 2040, and what the things are going to be. The economy is going to be, maybe business as usual. The economy might go into the tank. They might be really, flourishing. So we have to look at all different scenarios, how we can take those data and layer in and model it. And then develop the pathways. Like pathways, I mean, like take the scenarios and develop different pathways, how they can decarbonize. Is there going to be hydrogen economy in 2040? That might be the one pathway to do. There might be some another pathways, which are heat pump pathway, or there might be biogas. There are all different types of pathways that can be chosen depending on what's the corporation's goal is. And then finally, charting and reporting, take everything into, all into documented and provide a report. And that's kind of embedded as we go from target setting number 1 through number 6. And as I said, the step number 2 and 3 more consist of assessing the opportunities, and this is how we look at the emission reduction strategies. As we know, start with the least cost or high impact measures, layer in with incentives, and so that, that's generate that project savings, and take those savings and put into capital projects. That's the second step, right? You are already saving some amount of energy as well as cost, and some of these capital expenses could be offset with the cost you are saving, and then move all the way to electrification, which is more expensive than the capital projects, and that could be funded through the initial 2 different opportunities, and then more step into on-site renewable and storage, and then more grid interactivity, and final 2 steps are we're already there and we need some off-site renewable energy, some power purchase agreement with vendors, and then rest of the things could be done with carbon offset projects. All right, so now we'll hone into a specific project DNV worked on. This is a food and beverage industry. I'll go over quickly the organizational background and decarbonization goal. This is a global food processing company, and they were focused primarily on scope 1 and scope 2 reduction, 50% by 2030 and 100% by 2040. And the scope included developing carbon neutrality assessment for 3 of their global sites. And we're going to talk about one of the sites here in the US. And developing net zero pathways that for each site from those 6 chosen global sites. So project scope, we have to develop energy efficiency process optimization actions for each site and develop an energy balance model, look at different end use, and develop estimate of energy and carbon savings for individual opportunities. And of course, CapEx and OpEx are very important to achieve 2030 and 2040 targets. As I said, it's always not always about facilities, or it's not always about the decision makers. Both have to kind of come together to work to achieve this goal. So stakeholder engagement is really critical. And we also, facility people are important, so that because they are on the ground who are going to implement these opportunities. So we had engagements with both the teams and workshopping and making this analysis and moving this forward. And first, I'll just go, I'm running out of time here, and I'll just kind of quickly go over this. And this is a context analysis we did for potential pathways, because when you go in, we just ask them questions, have these workshops, and say, okay, what can we do, right? All come together and make a list, laundry list of. Then we just kind of say, what is the impact? If you take the traffic lights, green as in sure, and yellow as in uncertain, and red means no-go, right? So we took these criteria and say, okay, these are the options, and these are the impacts, and these are the costs, and let's see what we can decide and what we can do with this. So then we took this and say, okay, so now these, those analyses will inform these pathways. We looked at all these options. Now we decided on this 7 pathways. Electrification is one, hydrogen, green gas, biomass, carbon capture, storage, then we had a combo path one and separate one for geothermal, which we can see no for all the cases. And all these were decided based on if infrastructure is available, if there is a supply availability, is there, there are policy priorities in particular location or not, or there are any local issues, sector level type of issues that we have to deal with. Here's the savings. So after we decided on what we want to implement with this customer, we went over all the energy efficiency opportunity or decarbonization opportunity. As you can see, the cost along with CapEx and OpEx and the energy savings and the scope 1 and 2 emissions. Okay, so these are the rankings, as you can say, all for different pathways. As you can see, they are achieving, there you can see all those green line, 2030 is for boilers and hydrogen for 2035 and wind energy for 2035. And this is basically the prices, emission factors and prices that were taken into account while performing the pathway analysis. Okay, so this is critical path. We looked at this comparison of pathway for 2030, and as you can see, the scope 1 and 2 reduction potentials. As you can see, electrification 2 came to close to 40%. They were not able to get to 50% what they had aimed for. And the other one was the combination of biogas with electrification. And none of the other options were more than 20% reduction. And as we're seeing from more 2040, all of the pathways were able to meet the 100% goal. That's because of eliminating a lot of this scope 2 emissions. This is the energy consumption for different pathways, as we can see. And as we see, imported electricity is kind of going up, whereas other type of fuel have gone down substantially for 2040. Pathway for CapEx, and this is more energy efficiency cost as well as the new fuel or the pathway cost associated with each pathways. As you can see here, they're achieving the CO2 emission to 2030 by almost, this is a scope 1, by 100%, and as you go towards 2040, this is more of heat pump application, and mostly all 100% is achieved from 2030 through 2050. And similarly for hydrogen pathway, as you can see, it's more hydrogen in purple, and whatever energy efficiency or decarbonization measure has been implemented, and rest, everything from 2030 to 40 is more hydrogen. This is a combo one. This is something achievable as well. Just quickly, almost net zero by 2040 is feasible for these 5 sites, and 50% emission is hard to achieve. But they are still continuing to implement their energy efficiency measures, but they're going to reconsider about all other fuels, hydrogen, such as hydrogen heat pumps and electric boilers, after 2027, and which basically driven by a lot of these policies that will come through. That's all. Sorry to rush here, and took a little more time than expected.
Thank you. Yeah, thank you for broadening the perspective into all these strategic things. Our next speaker is Kevin Johnston. We're going to switch to this clean electricity side. Kevin's with Total Energies, and Kevin, take it away.
Thanks, Kelly. Good afternoon, everybody. Delighted to be here to talk to you today. My name is Kevin Johnston, Senior Account Executive with Total Energies. And I'm going to talk to you today about renewable energy options for industrial decarbonization. We'll do a little bit of Total's renewable commitment to show that we walk the walk, as well as talk the talk with our customers, a little bit of on-site and off-site renewable energy solutions, and some customer case studies. So Total is a global energy player, and we have a net zero emission goal by 2050. And to achieve that, we're going to be investing $60 billion over the next decade to get there, and to also help innovate the way and come up with new solutions and technologies. And we also have a goal of generating 100 terawatt hours of renewable energy by 2030. That's roughly on par with about 100 gigawatts of assets by 2030. Today, we have about 22 gigawatts, 15 gigawatts of which are solar, and it's a global footprint. And for those of you who don't know, Total acquired the C&I division of SunPower back in 2022 and was actually the majority shareholder of SunPower in 2012. That was the first investment in the US renewable market of Total Energies. So we've got 22 gigawatts of installed renewable assets, 4 gigawatts in construction, and 54 gigawatts in development. That's with about 6,000 employees globally, 1,300 projects in over 60 countries, so covering a lot of ground. So for on-site and off-site renewable energy solutions, I'll start with the on-site and spend most of the time with on-site. Most of the projects we do on-site are through power purchase agreements. That's where we own the asset, we develop it, we build it on-site and operate it and provide performance guarantees so our customers can focus on their core business or other decarbonization goals. And we tend to leverage the tax incentives a bit more efficiently than our customers. So we tend to do this in the public and the private sector as well. About 70% of our projects are PPAs. This is an interesting snapshot to show you globally for those of you guys who have operations around the US. This shows you markets that we can operate in for both standalone storage and solar and storage combined together as a function of the federal investment tax credit. The Inflation Reduction Act brought the ITC back up to 30%. It was on a downward trajectory, and also provided two pathways to get 10% ITC adder for being in an energy community, which is census-based and a function of your address, and then another 10% for domestic content, which is spurring a lot of manufacturing in the US to build the equipment and the materials necessary to build these projects. And so you can see with the darker green areas, that shows you where, just based on tariff analysis and project costs, where we can build these projects at the 30% ITC level. And then if we add an additional 10% ITC, you can see in the lighter green, new markets that starts to open up. And then you can see if we add another 10% to get to a total of 50%, that opens up even more markets. And so our policy team is heavily involved in going to these new and emerging markets to make sure that the regulatory framework is as conducive and helpful as it can be to foster renewables. You probably heard a lot about storage recently. I'd say we are attaching storage to about 70 to 80% of our projects. They help spread out the generation of the solar, and they help provide other benefits like demand charge offsets and energy arbitrage. We're also seeing an uptick in the interest in standalone storage in the markets. That could be for grid services. It could be for offsetting coincident peaks. So we're actually seeing quite a bit of interest in growth in that market sector. And then resiliency as well for folks that want to look at microgrid capabilities or a way to harden their infrastructure, especially with a lot of the fires that we've had in California. There's been incentives in place, put in place to help increase the amount of storage in high fire threat zone areas. This shows you roughly how we're able to bring storage into a project and increase the value of the project overall. You can't quite see it, but you've got this is a typical day for a customer. You've got the line on top is their load pre-solar. You can't see it, but there's a yellow line in the middle that is the solar production. And then I'm going to do some pinch analysis on the fly here and see how Dr. Kissock grades me. But one thing we can do is demand reduction. We can basically pinch that demand off from the customer right there by discharging the battery. You can see the green in the bottom is where we're discharging the battery. That reduces the pull from the utility and the associated demand charges. And so that's one way that we're able to improve the economics of the project with storage. And the other way is with energy arbitrage. So we're able to, you can see the green in the middle that is negative. That's where we're able to the solar is exporting, we're able to dump some of that into the battery that's charging the battery, and then we're able to discharge it, you can see on the right, during peak times where the energy prices are significantly higher. So that's between 4 and 9 o'clock. And so that energy arbitrage results in about a 16% increase in savings for this particular example, with about a 20% increase with the demand offsets. So you're adding some really significant economic benefit to the project with the solar and storage combined together. For offsite solutions, we have a separate team that's focused on utility and power plants across the U.S. And this is a great way to, if you don't have, if you're space constrained and you can't build an on-site project, or if you are building on-site, you can include a VPPA to help round out the rest of that carbon footprint that we can't offset with on-site renewables. And so with a virtual power purchase agreement, we're seeing a huge uptick in this offering where at a high level, we're able to build, let's say, a 200 megawatt plant in Texas, sell into the wholesale market, into ERCOT, and then we're able to generate RECs with that revenue and sell that to a customer in, let's say, Ohio, where they can't build on site, but they can buy these RECs. They maintain their same utility relationship, doesn't affect their relationship with their current utility, but they're able to buy those RECs from us in the long-term purchase agreement. So that's a great option. Physical power purchase agreements are similar, but those have to be built within the same ISO or service area, typically sleeved through the utility. But in that case, the customer is getting the actual kilowatt hour. They're buying the kilowatt hours, taking ownership of it, and the associated RECs. So some customer case studies. This is a project that we announced recently in the cement industry. Obviously, that's a huge carbon footprint that's had a lot of attention today. This is with Holcim, a project with Holcim at their Portland cement facility in Colorado. It's a 33 megawatt ground mount solar array paired with 19.2 megawatts of storage. It's a 2-hour battery, so it's about 38.5 megawatt hours. Offsets 40% of the plant's needs. We're also doing with Holcim a project in Belgium for another cement plant, 31 megawatt floating solar photovoltaics. That's about 70 acres of solar on water, which is pretty awesome. A mining company, a minerals company, Emiris. This is a project in California, 14.8 megawatts in Santa Barbara County with a 1.8 megawatt, 7.5 megawatt hour battery attached to it, offsetting 50% of the needs annually. And then also a project with Chevron. This is an exciting project that was brought online about 5 or 6 years ago. And this was under NEM 2. So instead of having a 1 megawatt limit under NEM 1, we were able to size it to load. So we've got 35 megawatts under NEM 2. And it also participates in the LCFS program. And that's adding a lot of value to the project that helped move it forward. And at the time, it was the biggest net metered project in the country. And it still might be today. So just a little flavoring of actual projects in the last few years. So thank you.
Well, I have the hardest job here, which is to cut off these fantastic speakers. Let's give everybody one more round of applause, please.